Good afternoon, everyone, and welcome to a new session of Science in Progress. In Science in Progress, we take you through a journey of the latest scientific research in the UAE every Monday and Wednesday, with this week being the last week of the program. So after today's session, we have one more session on Wednesday at 2 p.m. Please don't forget to register. Before we start, if you have any questions, please post them in the Q&A tab. Our guest today is Dr. Francesco Arneodo. Dr. Francesco is a professor at New York University, Abu Dhabi, and he is an experimental physicist with his main interest is in subatomic particle detection with applications in astrophysics, particle physics, and cultural heritage. Dr. Francesco is going to tell us today about research in the field of physics in general and the universe and dark matter more specifically. Dr. Francesco, it's good to have you here.
Thank you. Thank you for inviting me. I hope you hear me okay, and I'm going to share my screen right now with my slide. So just a second.
Great.
Okay. Okay, I'm sharing the screen. I'm starting this short presentation in which I will try to tell you what it means to study the universe from underground and some other things you can do with particle physics. So thank you for the introduction. I am indeed a professor at NYU Abu Dhabi. I joined NYU Abu Dhabi in 2013, and I'm going to give a sense of why I chose to do science. And so these are a few slides as an introduction of my career. I was born in Turin, Italy, which is, for those of you who follow soccer, is the city of Juventus. I went to study classical studies. So in my high school, I studied Latin and ancient Greek, and then I chose to do physics at the university. But actually, when I was studying physics, I also was very excited about climbing, mountaineering, and so climbing on rock, ice, and whatever it could be climbed. And I thought that I would do that as a profession, which is an exciting but slightly risky job. And this is in this image you find something, an example of what the kind of things I was doing when I was younger. Okay, so I was telling that I wanted to do as a profession the mountaineer, but then during my thesis work, at the end of my university career, I did the thesis, an experimental project. I actually discovered that experimental physics is almost as exciting as climbing, but slightly less risky. And actually, I was working on cosmic rays. And at the Gran Sasso laboratory. The Gran Sasso laboratory is in Italy. It is beneath a mountain. Actually, but one of these experiments was at the time on top of the mountain. And you can see, if you see my cursor, you can see this small scheme at the bottom of the slide in which you see the mountain, and these three small dots are the experimental holes inside the mountain. And on top of the mountain, there was this array of detectors that was supposed to study cosmic rays. So the question is, what are cosmic rays? And so cosmic rays are a constant and uniform flux of particles that hit the top of our atmosphere, and most of them come from our galaxy. And most of them are nuclei of helium and hydrogen. And they have been hitting the atmosphere since the beginning of times, and they form a constant flux of radiation, which is connected life on Earth, is connected with evolution because they contribute to the mutation mechanism that is part of the evolution of a living organism. And they're also connected with the weather, but this would be the subject of another meeting, perhaps. You can measure cosmic rays. I was measuring cosmic rays at the time of my thesis. I'm still working somehow with cosmic rays. And if you come to my office at NYU Abu Dhabi, you will see this small detector which you see on the right side of the slide, which has been designed by my team and assembled by students of NYU Abu Dhabi. And if we put this detector outside, we could see as much as 100, more than 100 particles per square meter per second. And actually, this is what we did a couple of years ago. We did a measurement of cosmic rays, which we published, of the cosmic rays in Abu Dhabi. But my main interest from the time of my thesis somehow switched from cosmic rays to something else. And to see this something else, I had to move underground. So I decided to move my interest from outside to the inside of the mountain, where the core of the Gran Sasso laboratory is. So this is a short description of the Gran Sasso laboratory. If you look at the bottom right of my slides, you will see this small red dot is where the laboratory is not far from Rome in Italy. And actually it's on the side of a highway tunnel which connects Rome with the Adriatic Sea. And here you see an artistic view of what's inside the mountain. The laboratory is composed by 10 caverns. Each of them is about 100 meters long, 15 meters wide, and 20 meters high. And it's still the world's largest underground scientific laboratory, which hosts currently about 15 experiments on neutrinos, dark matter, and other interesting physics phenomena. It is under 1,500 meters of rock. And here you can see an image of a visit of students from NYU Abu Dhabi to the laboratory a few years ago. And the question is why we would go underground to do physics. Well, I told you about cosmic rays. Cosmic rays are very nice to study. They tell us a lot about the universe, but sometimes they are a noise. You want to study something which is not cosmic rays, and you want to filter them out. So the only way to do that, go inside a mountain or inside the deep sea or inside deep ice. So to put a screen, a shield behind you and the main flux of cosmic rays. So some of the particles, cosmic rays, actually will not be disturbed by the rock and will pass it without a problem. And some of these particles we know, and they are the muons and mostly the neutrinos, and these again would be the subject of another meeting. But we think that there are other particles that go through the mountain, go through the rock, and but we don't know them yet. We just think they are everywhere. So the question is, what are these particles? And the answer is also the answer to the question to where is the main mass of the universe. So if you see this image of a galaxy, this is the beautiful Andromeda galaxy, you see that you would think that the mass of the galaxy is mostly concentrated in its center, in the bulge of the center. But already many years ago, in the 30s, the guy on the bottom right, an astronomer, a Swiss astronomer called Fritz Zwicky, already understood that the universe contains way more mass than what you see with an optical telescope. And actually, with a rather simple calculation, he showed that the galaxies were moving as they had much more mass than what you see with an optical telescope. But for many, many years, this observation was not really considered until the 80s, when the lady in the bottom of the slide, Vera Rubin, who passed away a few years ago in 2016, led a team of scientists which measured the velocities of stars as a function of their distance from the nucleus of the galaxy. Now, if the galaxies were had a mass distributed like we see in this picture, so with the most of the mass in the center and just a slight fraction of the mass in the disk, then the velocities of the stars should follow this blue line. So it should decrease as further out from the center. So But actually, the team of Vera Rubin discovered that the profile velocity of most galaxies were actually following a different law. So you see that all these curves actually show a more or less constant velocity after some distance from the center. And the only explanation we have for this is that actually the distribution of the mass in the galaxy is not what you see, but is a kind of halo, a spherical halo, which is all around the disk of the galaxy. And one of the explanations is that this halo is comprised of particles we haven't seen, we haven't seen measured yet in a detector, and we call them weak interacting massive particles. So in short, WIMPs. So these could be the explanation of the anomalous behavior of galaxies in terms of gravitational rotation. Actually, this is not the only evidence. So for brevity, I'm not going through all the evidence we have for the existence of dark matter, but let me show this simple picture in which we show what we know now of the mass distribution in the universe. You see that the small yellow part, the 5%, is what we call ordinary matter. So the matter we are made of, our stuff is made of. The rest of the mass and energy content of the universe is something we don't know. 27% is what we call dark matter, I just spoke about that, and 70% is something which is even more mysterious. We call it dark energy. And again, that would be the subject for another meeting, perhaps. So if dark matter is really made out of WIMPs, how we can detect these particles? And I'm a particle physicist, and many particle physicists have been thought about that for a long time. And so one hope to measure these particles directly will be the following. So suppose that as we assume the mass of the galaxy is really distributed in a big halo around the main disk of the galaxy. If we zoom a tiny fraction of this disk, we will find our solar system, which is just a small part of the Milky Way. The solar system, we know, it's moving in the galaxy at around 200 kilometers per second. So because there is, we think, this sort of fog of particles, of dark matter particles, as if our planet, our solar system, were moving inside this fog of particles. So we would see these particles coming towards us at about 200 kilometers per second. Now, suppose we have, now we hope that some of these particles will eventually hit one nucleus of ordinary matter. So this is the WIMP, which we see coming to us at around 200 kilometers per second. And this is, for example, an atom of xenon. Xenon is a gas that you find in the atmosphere. It's a noble element. And of course, as all atoms, it's composed by an electron cloud and the protons and neutrons in its nucleus. So if the WIMP it hits a nucleus of xenon, then the nucleus will move a tiny bit inside its element. And why we choose xenon? Well, I can answer that question later, but there are a number of reasons why the xenon would be a good target to see these particles. So suppose we collect many atoms of xenon, of course, and we put them in a special place, which is a tank which would contain xenon. And to make xenon liquid, we needed to cool it down at minus 100 degrees centigrade. So this tank would contain liquid xenon and would have its bottom and its top covered with special devices which we call photomultipliers. So if our supposed particle would hit a nucleus inside this liquid, well, the nucleus would move, and also it would generate some free electrons inside the liquid. So because of the photomultipliers, we would be able to see a tiny flash of light, which is emitted by the nucleus moving and also by the electrons, which would be drifted towards the surface of the liquid. And we could analyze these signals. We could see and analyze these interactions, these collisions. So what I just described is a device which is called in physics jargon a double phase time projection chamber. And collaboration, my team, or the collaboration I am part of, already built 4 of these detectors. We started in 2004, more or less, with a few kilograms of liquid xenon. Then we call that xenon 10. Then we moved to 100 and some more than 100 kilograms of liquid xenon, and we call that xenon 100. Then we recently operated a bigger detector called xenon 1 ton, which had 3.2 tons of liquid xenon. And finally, we just built and we are about to operate a very big detector with 8 tons of liquid xenon. All of these detectors work exactly with the techniques that I just described. They're just bigger and they are more cleaner from the point of view of inner radioactivity. So let me show a few images of xenon 1 ton, which is the detector which we just stopped operating, and also show the place, I mean the installation here on the right of the detector inside the hall B of the Gran Sasso laboratory. We need to be underground, we need to be protected by the mountain because we are looking for very rare signals. So we suspect that if dark matter really exists and it is made out of these particles, we would see very few interactions in one, or maybe just one interaction in 1 year of operation. And if you remember what I said about cosmic rays, well, we would see outside of the mountain, we would see hundreds and hundreds of collisions because of cosmic rays if we place the detector outside. That's why we need to be protected by the mountain. What you see here on the left of the picture is actually a big water tank which contains the cylinder, the cryogenic cylinder, which contains the liquid xenon. And water is further protecting the detector from the residual radioactivity, which is even present underground. On the left, you see a picture with all the logos of the collaborating institutions to this collaboration. We have about 160 scientists from about 20 institutions from 11 countries, including the UAE with NYU Abu Dhabi. We operated this detector for about 1 year, let's say, and you see this curve is the accumulated amount of data we collected. And let me anticipate the conclusion. Unfortunately, we did not see dark matter yet. So now I'm showing a little bit of a technical plot, which I can explain later if there are questions. But essentially, this shows that each of these dots is one interaction that happened inside our detector. And this bigger dot represents the ones we could be possibly dark matter interactions, but unfortunately they are not. They are just too few and compatible with the natural background of our detector. So we cannot say that we discovered anything yet. And this is why we are actually building a bigger detector, this is a bigger detector, which is xenon N ton, which you see here on the right during the construction phase. And you see that people are wearing masks and suits, not because of the virus, but because they need to build this detector in a very clean condition, because even a fingerprint would leave the traces of radioactivity, which would damage the data taking of the detector. This new detector is about to start operation within the year, and it contains a total mass of 8 tons of xenon. And you can follow our activities on Twitter, on Instagram, and on Facebook. So stay tuned if you're interested. Then, of course, I have to say that dark matter is maybe not the explanation for what we see. Maybe there are other explanations. Actually, there are other models that somehow would explain what we see in terms of behavior of galaxies. So what I'm going to say is very important. Dark matter is an hypothesis. It's a model which can explain effects, but it may be wrong or it may be right. So only experiments like the one we are doing and others can tell us the truth, if it is a good model or a bad model. And that's the way science works. Science works testing models, not just making hypotheses. By the way, sometimes you look for something and you find something else. And last year, we published a very nice paper which made the cover of the prestigious magazine Nature. And because our detector is so sensitive, we could observe a very rare decay process of xenon 124. It's a very slow decay process. Actually, it's what we call the half-life of this decay, which is a quantity that characterizes the speed of a radioactive process, 1 trillion times longer than the age of the universe. So you can imagine how difficult it could be to see this effect. And if you're interested, there is a YouTube video in Arabic that explains the measurements we published last year. So one question that people might have is this one. So what do we get out of research? What I describe is basic research, is research not necessarily aimed to solve any specific practical problem of our life. And you see an answer to this question in the picture on the left. But let me be more specific. So good research is never useless, because even if you don't find anything, but you are doing something very difficult, like trying to solve the mystery of dark matter, you will need top for that. You need special tools, special detectors, which needs special technologies. You need top people. And so you need to train these top people, and so you need top students. All this, you will come very useful at some point. And just to make some examples, Michael Faraday, the famous scientist who in the 800s studied electromagnetism, was certainly not trying to improve candles. He was just playing around with the laws of physics. Another example, all medical diagnostic tools like the one I showed in the first slide, a few slides ago, they all come from atomic and particle physics research, like magnetic resonance, positron emission tomography, CT scan, and there are many others. Cancer can be treated with particle physics. And I encourage you to watch another video on YouTube of a public talk of mine did a few years ago on how you actually battle cancer with accelerators, with particle accelerators, and which is a very powerful technique that can save a lot of life. Then among these many applications, there is one that I like very much, which is this one. You can see a strange instrument in this picture, and which is positioned just in front of an ancient manuscript. And this object is called X-ray fluorescence spectrometer, and has been built by a collaboration between some colleagues in Florence and my team in Abu Dhabi. And this is the way it works. So you see here in the picture on the left, you see this brass object, actually an emitter of X-rays. So you emit X-rays, these X-rays hit the surface of an object, could be a manuscript, could be a piece of ceramic, it could be a painting, whatever you want to study. And these X-rays will knock out some of the electrons inside the atoms of the surface. If you knock out an electron from the shell of an atom, then some other electrons will immediately jump to fill this void. And as a consequence, you will get other X-rays emitted from this atom. But the beauty of this is the energy of these X-rays is very much connected to the type of atom. So if I measure the energy of this X-ray, I can tell whether the atom that emitted them was copper, was calcium, was potassium. So I can essentially analyze the surface of a painting in terms of its elemental composition, which is very important when, for instance, you want to restore a painting, you want to know if that painting of that artwork is authentic or is a fake. And this is an example which I taken from a research we are doing in collaboration with Louvre Abu Dhabi, in which we analyzed an illumination you see here on the left with this technique, exactly with the instrument that I showed you a few slides ago. And this image here is a spectrum of energy that we get out of this measurement. And if we want, we can select only, for instance, the copper, and we obtain an image on the right, which is exactly the image of the manuscript, but putting in evidence that this light blue oval is actually made out of copper. And I can do the same with other elements like gold, for instance. Now, I just take another example, which has been done by my colleagues in Florence. This is a painting of the famous painter Raffaello, famous Renaissance painter. And people, I mean, people in the museum had to restore and actually understand how better protect this painting. So they needed to analyze a small fraction of it, and they did using the same technique, so they could essentially make images of this painting in calcium, in mercurium, in lead, potassium, and copper. So exactly mapping out the presence of those elements on the painting, understanding what kind of paint the painter used when he created this masterpiece. So just to conclude, my team and I and many other people in the world, we do basic research. So we are not especially interested in applications. We're not trying to improve candles as in the example of Faraday. But although this might seem sometimes useless, actually basic research is very useful. In fact, it's one of the most useful activities of humankind. But the fact is that we don't do it because it's useful, but we do it because it's actually a lot of fun. And it's really incredible to work in a team and to try to push forward the frontiers of knowledge and to use very refined technologies to do that. So this is the end of my presentation, and of course I'm open to questions, and if you want to ask me something later, you can email me at this address or tweet me at my account. All from my side.
Thank you, Dr. Francesco, for such an interesting presentation. I have one question, like what inspired you to choose this field, dark matter, especially that you said that it's something that we don't know if it exists. So what drives you to do research on such topic?
Well, it is true that we don't know if it exists, but precisely this fact represents a big challenge. So it's one of the biggest challenge in astrophysics and in particle physics. If you discover dark matter, well, you solve one of the biggest mysteries in the universe. Let me pull up one of the previous slides. This represents our present knowledge of the universe. So we know the 5% of where essentially where we live. So wanting to know what is outside, what is the rest, is a big drive to do research.
Thank you, Professor. We'll take some questions from our attendees. We have a question here from Mansour. He says, what advice could you give to physics students, and is physics a required major in the future?
Physics will be always a required, I wouldn't say major, a required knowledge. So I think that knowledge is shifting. So we are used to think about doing chemistry, doing physics, doing biology, you know, fine, of course, but we are already actually in an era, in a time where you need many disciplines to approach problems. Whether they are, you know, specific problems or global problems. For instance, take global warming, climate change. There is no way a single discipline can tackle that. You need interdisciplinarity. You need people, scientists, to talk to each other, from chemistry to physics to biology to economics. So my advice, if you're passionate about physics, study physics, but try to be as open as possible to other disciplines. I ideally try to study more than one discipline.
We have another question here. Considering the fact that cosmic rays comprise of hydrogen and helium nuclei, is it correct to assume that the sun is the only source of cosmic rays?
Actually, this is a very good question. Actually, the sun is a source of some cosmic rays, but they are very low energy. And actually, most of the particles emitted by the sun are trapped into the outer layers of the magnetic field of the Earth, and they are conveyed to the poles because they are really low energy. And most of the particles that comprise cosmic rays are actually, we think, emitted by a high energy phenomenon in the galaxy, like supernovae. And when we see a cosmic ray in our detector, it is generated by a particle that has traveled for millions of years in the galaxy, deviated by all the magnetic fields in the galaxy itself. So it has been emitted many years ago, and then moved around, and somehow comes to our planet. So it is correct that the sun is a source of cosmic rays, but what we see in our detectors on the ground is mostly coming from higher energy sources.
We have another question here. Can you elaborate on more on other examples of diseases that may be treated using particle physics?
Well, you should probably, I'm not probably the best person, because again, this is an interdisciplinary collaboration. So I'm personally not doing medical physics, but let me elaborate on, well, first there are two things that there are a distinction. Particle physics techniques in medicine is divided in two main branches. One is the diagnostics, so imaging. So for instance, take a positron emission tomography. You inject a radioactive tracer in your body, and this tracer goes to the cells, to the organ that you want to image. And this radioactive tracer emits positrons, which are the anti-electrons. They will annihilate with an electron, and you get two gamma rays that allows you to pinpoint exactly the origin of their source. So you can map in 3D the organ that you want to see. So this is an example of imaging, of diagnostics. Then you have treatment, and the treatment is essentially the use of ionizing radiation. It could be electrons, could be X-rays, or could be hadrons, protons, to target, for instance, cancer cells. And I think this is the main area of medical treatment with particle physics tools. And just let me elaborate slightly on the hadron therapy. So the therapy that uses protons or ions to target cancer cells. And this is a beautiful technique because if you study physics, particle physics, you will learn that protons deliver their energy at the very end of their range. So a proton will will destroy only the cells in which the proton itself is going to lose its energies at the end of its path. Whereas an electron or a gamma ray will damage all the tissue in between the source of the gamma ray and the target itself. So protons are a very powerful way of curing cancer. Of course, not all cancers can be treated like that, because if you have metastasis, it becomes difficult, but if a tumor is localized, this is a very powerful tool. The problem is that it's quite expensive, but now the technology is more affordable, so more countries are building these kind of facilities, which are extremely good investment for a country.
Thank you, Professor. That's very interesting. We have a question here, and I think this is related to your point on basic research. How can you balance between the expenses on these experiments and the unassured results of the outcomes?
Okay, this is another very good question. Apologies for this phone that is ringing that I cannot stop. Yes, this is a very good question. This is sometimes scientists have a very good, what they think they are very good ideas. So for instance, to make an example from the past history of particle physics, the discovery of the Higgs boson. Some of you for sure remember that in 2012, there was a big rumor in the news because the scientists at CERN, the facility in Geneva, and actually had a picture of it here at some point. Yes, this picture on the right is one of the detectors at CERN, which is part of the LHC accelerator, and this detector was one of the two detectors that discovered the Higgs boson, which is a particle foreseen by theory, but no one ever measured it until 2012. So the construction of this facility to build, the construction of the facility to discover the Higgs at CERN costed billions and billions. And then the scientists had to go to their governments and convince them that it was a good investment. And of course, typically in the governments, not everybody is a scientist. Sometimes there are no scientists in the government, and they have to be convinced that this is a good way of putting taxpayers' money. And so I was saying that proposing big experiments to ministries and governments is difficult, and of course it's a society effort. It's political effort, and we should make sure that our scientists are well prepared, and the people in the government are also well prepared to understand the reasons of scientists. Even though when they are proposing something which is very expensive, and sometimes scientists might be wrong. It's not that you have always to give money to scientists. Sometimes they should be said no, because something is really too much expensive. And so this is anyway, it's a difficult process because experiments, especially in physics, but also in astronomy, are getting bigger and more expensive. And there is a last thing to say. All big experiments have to be international collaborations. It's very difficult for a single country now to afford very difficult and expensive experiments.
We have a lot of questions here. We'll take one or two more questions. There is a question here. You just mentioned the Higgs boson particle. Can it be used to help to detect dark matter? And are there chances of the super collider detecting dark matter?
Okay, another very good question. So, this is a complicated answer. I'm not sure I can, it entails a lot of theoretical physics. So indeed, well, the Higgs boson is the particle which mediates essentially the mechanism by which all other particles get mass. So if dark matter particles have mass, like we know they should be somehow connected to the Higgs boson. And it's not 100% sure. I mean, it's not a certainty, but they could be connected with the Higgs boson. The other thing is that indeed, dark matter could be produced at the accelerators. So far, there is no evidence for that. What you would see, you would not see directly the particles, but you would see some energy missing in your events, in your construction of the complicated events you have in particle accelerators. So far, there is no hint of that, but LHC is still working, and actually it's going on an upgrade phase, which should increase its efficiency and its energy. So it might be that in the next few years we'll find something through the accelerators and or through the experiments like the one I'm participating in.
Okay, we'll take one more question. What is the link between dark matter and black holes? Recently, scientists were able to come up with a photo using AI. Do you think dark matter is something that can be detected in a similar way?
Well, I think the question refers to the picture of black holes that was published a couple of years ago or 1 year ago, I don't remember. Black holes essentially might be composed of dark matter, meaning that a black hole is a vortex in which a lot of mass precipitates. And of course, among this mass, there is also dark matter. But other than that, I don't see a direct connection. Maybe I ignore it, but I don't see a direct connection between black holes and dark matter. They're two distinct things.
Thank you, Professor. Professor, if you could tell the students, what does it take to be a scientist?
Yes. Well, the answer might differ. The answer might differ from person to person, but in general, I think that well, you should be curious, and you should curious and motivated to study and work a lot. And in science, and also something else to say, in science, there is not just the scientist, the person that, in a white coat is in his or her lab doing strange things. I was telling before that experiments, especially in astronomy and in physics and astrophysics, are getting bigger and bigger. They are enterprises. You need to design, to conceive, design, build and operate a big experiment. You need hundreds, sometimes thousands of people. The LHC and its experiments was the largest human enterprise since the Manhattan Project. So, and this is true even with smaller experiments. You need a lot of competencies, a lot of skills. So to participate in science, you can even be sometimes an economist, a social scientist, because there are so many skills that are needed that really is not because you choose a field which apparently is not related to science that you are cut out of this project. Actually, because of the lot of money that you need, and also the lot of people you need different skills. For instance, at CERN, in all large collaboration, there are psychologists, because you need to handle all the human dynamics in large groups. So really, but anyway, if you have to say just a few words: motivation, curiosity, and hard work.
Thank you so much, Professor, for your time and for answering our questions. This was a very interesting session. I think it was also interesting because we don't have many researchers in the UAE doing this kind of research specifically. Would you like to add anything before we end the session?
Well, again, I posted my email address, and feel free to share it with the students if they want to know more. I'm happy to answer, and I wish a great career to everybody.
Thank you very much, Dr. Francesco, and thank you for everyone who attended the session and for the questions, the good questions that we had. This session is going to be is being recorded, and it's going to be on YouTube if you want to watch it again or share it with your friends. We're going to have our last session of Science in Progress next on this Wednesday, actually, at 2 p.m. with Dr. Gulfaraz Khan on viruses and their relation to cancer. Please go to the link and register if you're interested in attending. Once again, thank you very much, Dr. Francesco, and thank you to everyone who attended the session. Thank you.
Thank you for inviting me. Thank you for organizing this, and thank you to all the attendees.